What's up, everybody? Welcome to the NeurIPS pre-show. I'm your host, Harpreet Sahota, hacker in residence at Voxel 51, and I'm with my co-host, Jacob Marks, who is a research scientist at Voxel 51. We're joined by Vishaal Udandarao, author of the paper No Zero Shot Without Exponential Data, Pre-Training Concept Frequency Determines Multimodal Model Performance. This paper was accepted into NeurIPS 2024. Vishal and his co-authors have studied what zero-shot generalization really means for multimodal models like CLIP and Stable Diffusion. These models have absolutely changed and revolutionized tasks like image recognition and text-to-image classification, and they all kind of boast this impressive zero-shot capability. The idea is that they can perform well on tasks that involve concepts that they actually haven't explicitly been trained on. But is this zero-shot performance truly due to generalization? And that's what this research paper that Vishal will talk to us about is going to explore. They examined the performance of 34 multimodal models on various tasks, including classification, retrieval, and image generation. And then they looked at the frequency of the concepts that were used in these tasks within the massive data sets that the models are pre-trained on. The key finding is the concept that frequency in pre-training data strongly predicts zero-shot performance. This suggests that rather than generalizing, these models might simply be recognizing concepts they've already seen during pre-training, even if it wasn't in the same context as the zero-shot task. This is highlighted by the log linear relationship they observed. Model performance tends to improve linearly as the frequency of a concept in the pre-training data increases exponentially. The research even found this trend when controlling for factors like similarity between pre-training and test data, and even when using entirely synthetic data set. This suggests the need for massive amounts of data to achieve even linear performance improvements, and is a fundamental issue for current multimodal models. So as you listen to Vishal's presentation, consider the implications of his findings. How should we think about zero-shot generalization in the light of this research? What does it mean for the future of multimodal models, and how can we address these challenges posed by the long tail of rare concepts? Vishal, thank you for being here, and go ahead and take it away.
Awesome. Thank you so much for the introduction. So like Harpreet mentioned, I'm going to be talking about our NeurIPS paper, No Zero Shot Without Exponential Data. This was joint work with a lot of amazing collaborators from Cambridge, Oxford, and Tübingen. And in this work, let's start with a simple question. What is generalization, right? In the olden days of classic machine learning, we used to have a training data set, train a model on it, and then test it on a held out test split. Back then, we had these very small scale and controllable training data sets, and we could manually inspect what was in there. And so we knew that what was in the test set was held out and unseen from the training set. However, then training sets started getting bigger and annotating them started getting costlier. So people started thinking about different kinds of generalization beyond the standard generalization I just showed. One way was this notion of zero-shot learning or zero-shot generalization. The basic premise of this was that you would train your model on a bunch of different classes during training. However, at test time, you would see totally unseen classes. And the main premise was that you would be able to generalize by learning different attributes from the training classes and then utilizing them at test time. So that was the sort of basic notion of zero-shot generalization back then. However, in 2021, CLIP comes along and changes this notion. So what CLIP does is it trains a model on a large image text data set. And the simple objective is to match image text pairs that are aligned and push image text pairs that are not aligned farther apart. And after training, it comes up with this notion of zero-shot transfer, where you can simply take the class names of an unseen data set at test time and use them for prediction as you would do in a standard zero-shot classification way. Note that this is different from the previous zero-shot generalization settings, because here you don't even know what you're training on. The data sets are so massive. And if you actually look at how many times the CLIP paper mentions zero-shot, it's a lot, right? So in general, what I'm trying to capture here is that the term zero-shot has diffused over time. And a big consequence of this is that we really don't have any idea of what's in these training data sets anymore. And that's why we are not even sure whether this term zero-shot makes sense anymore. So our goal in this paper was to take a sober look at the zero-shot generalization of these multimodal models. We operationalized this goal with a simple research question. The question is, how is the performance of multimodal models on certain concepts influenced by how often those concepts occur in the pre-training dataset? So what we're going to do in this entire presentation is going to be very simple. I'm going to take a bunch of concepts. I'm going to figure out how often they occur in the pre-training datasets of these models, and then sort of try to find a correlation between model performance on these particular concepts with the frequency, right? And that's exactly what I'm showing you in this plot. So before we dive in, I'm going to tell you what we are looking at here. So the first thing we are looking at is a bunch of concepts, right? Let's say we get about 5,000 different concepts from different downstream tasks. What I do here is I compute how often that concept occurs in the pre-training dataset, and that's what's on the x-axis. And on the y-axis, I measure model performance based on these different concepts. Obviously, we have a lot of concepts, so we need to bin them, and that's exactly how I arrive at these different bins on the plot. So 10 different bins means that we average out the per concept performance within a bin and look at the frequency on the x-axis and the performance on the y-axis to look at this. And across different tasks, across different models, across different data curation strategies, across different sizes of data sets, we observe a striking trend. All of these plots show a linear trend on a log linear axis. What this means is that if you want to linearly improve performance on the y-axis, so linearly improve performance of your model, you need to exponentially increase the amount of data you have for a particular concept. And you can see that this is consistent across all the different plots we have here. So these are for CLIP models. We also see the same results for text to image models like diffusion models and so on. For brevity of presentation, I've skipped those results, but you can look at them in the paper. So just to reiterate from those set of plots, the key finding of our paper was that there is a log linear scaling between how often a concept occurs in pre-training data and how well those models perform zero shot on those concepts. And the more striking finding is that you need to exponentially increase the amount of data you have to just linearly improve performance on the y-axis. And this suggests highly sample inefficient learning of our current multimodal models. One could ask, well, how robust is this result? Are there certain confounders you need to think about? And in our work, we control for two very important confounders. The first one is similarity of pre-training samples to downstream samples. Here, the premise is basically that, well, you could simply be seeing more samples that are similar to downstream datasets when you have higher frequencies, and that's why you see these trends. And the second premise is that, well, these are all natural distributions, but in the future, we are going to have a lot of synthetic data out in the wild. Will your results still hold true in such a case? And we do specific controls for each of these confounds, and we observe exactly the same trends across both these as well. When we control for similarity of samples between pre-training and test datasets, as well as when we control for a purely synthetic data distribution. Even here, we see that the log linear scaling trends hold exactly. So one key takeaway from all of the results I've shown you so far is essentially that models currently really underperform on long-tailed concepts. By long-tailed, I mean those concepts which are underrepresented systematically in pre-training datasets. And to sort of foster future research into trying to get models better on long-tailed data, we collected a truly long-tailed test dataset called Let-It-Wag. Here, we essentially took the 290 most infrequent concepts in around 400 million from our analysis, collated them together, and created a classification dataset, as well as used different prompts to test text to image models on this set of long-tailed concepts. I'm going to show you the results of how these look like. So the first is the Let-It-Wag classification dataset. Here, remember that the task is classification across 290 classes. The basic premise is that these classes are very long-tailed, so all models should perform poorly on them, and that's exactly what we see here. So in this plot, I'm showing 50 different CLIP models that have been pre-trained and released openly, and I plot their performance on Let-It-Wag on the y-axis, and on the x-axis, I plot the ImageNet accuracy. And you see that all of these models systematically underperform on the Let-It-Wag accuracy, further suggesting that the problem of long-tailed classification for multimodal models is prevalent across different model sizes, different model capabilities, different data curation strategies, and so on. And hence, these results suggest that we need to really be thinking about how can we have better algorithms for improving performance on long-tailed tasks. We also show the performance of text-to-image models on our Let-It-Wag test set. Here I show you qualitative results. There are also quantitative results in the paper, but essentially you can see from here that these two long-tailed concepts, Chuck-Will's widow and ocarina, if you try to prompt these diffusion models to generate images of them, they systematically generate images that are not at all aligned to the concept. Again, showcasing that these models do not really perform well on the tail, and they're really overfitted onto this head of the distribution of the image text data sets that they're pre-trained on. So that brings me to the sort of end of the quick presentation of what we've done. There are a few open questions that I'd like to ask people to be thinking about. One is, what is the effect of model scaling? We've shown plots across different model scales, but we did not do a systematic analysis of how model scaling, both in compute as well as number of parameters, leave us with respect to the log linear scaling trends we've seen. Another aspect which is super important, I think, is this notion of compositional generalization, because in our work, we only looked at concepts in an atomic manner. However, we do know that people are interested in combining these concepts and looking at tasks that involve these compositions. And finally, I'd like to ask and sort of bring some food for thought about what are effective measures to do data curation to combat this long-tail nature. A few strategies that seem plausible are, for example, retrieval augmentation or better balancing of the pre-training data sets and so on. And that brings me to the end of the presentation. Thank you so much for the attention.
Vishal, thank you so much for the overview of your paper. Really interested to get a little bit more into the work. I'll turn it over to Jacob to see if Jacob has any questions, and then I'll proceed with some of my questions.
Yeah, awesome work. Really appreciate this and enjoyed the presentation. One high-level question and then one very nitty-gritty question. So at a high level, what is a concept here? Like, what do you mean by a concept, and how general is that notion?
Great question. So we thought about this hard and long about how we should define concepts before we did the study. And the way we did this was to look at it from a practitioner's perspective. So how do practitioners use these models? They essentially test it on a bunch of downstream tasks and then figure out if they want to use these models for certain use cases. So we essentially collated a bunch of very popular downstream datasets. So we took about 27 different downstream datasets and then took all of the concepts that were prevalent in these datasets. So for classification datasets, for example, we simply took the class names of those datasets. And for retrieval and text-to-image datasets, we took those text captions and did like a spacey parse for objects and verbs, and then collated all of them together to get about 4,000 concepts in total.
Interesting. Very cool. And the nitty-gritty question is on the plot that you had showing ImageNet performance versus performance on Let-It-Wag. There are two different line fits there. What do those two different line fits represent?
Yeah, so this was one sort of question about whether this is the right visualization. In the end, we chose this because this is essentially showing that the stronger a model is, the sort of more it's closing the gap to the Let-It-Wag ImageNet line, right? So essentially, by stronger, I just mean better on ImageNet as a proxy. The problem, however, in this sort of a plotting style is that there is an upper bound of 100. So in some sense, if you look at previous distribution shifts work from, for example, Ludwig Schmidt and other groups, they always plot a differently scaled axis. And what you would then see is if you change the scale of the axis, all of these lines would lie on a line, essentially. So instead of having these two different plots, two different curve fits, you would see a single line to sort of showcase and hammer down the point that all of these models consistently underperform on Let-It-Wag compared to ImageNet. So essentially, this is more a visualization artifact than anything else, I would say.
Gotcha. Thank you for clarifying. Harpreet, I'll pass it over to you.
I just love the name of the data set, Let-It-Wag. I think it dawned on me halfway through the paper. I was like, oh, wait, long tail, Let-It-Wag. All right. Yeah, that was.
Yeah, I was really proud of coming up with it.
Yeah, no, that's an awesome name. You know, Jacob asked a question about the concept. I'm wondering what was your, I guess you kind of alluded to it, like the process for selecting like the concepts, like any inclusion criteria that you might kind of explicitly lay out for us? And were there any like challenges that you faced in curating a data set that was like specifically focused on this long tail?
Yeah, great question. So there were two parts of collecting this data set, right? So the first part is how do you ensure that the concepts you collect are diverse? Because in general, if you think about the long tail, it could be that a lot of those concepts are just very clustered together and they're not diverse enough. So the first challenge was in curating this concept list. And then the second challenge was once you had this concept list, how do you curate a set of test set images that are sort of non-contaminated with respect to pre-training data sets? I'll talk about both of them in detail. So the first challenge about the diversification of these concepts, the way we approached that was to sort of first take the bottom 500 concepts in terms of frequency, and then have a filter with respect to annotations of different types of images. So for example, we had different annotations of, we need to have animals in there, we need to have aircrafts in there, we need to have different sort of meta concepts in there. And then we did a sub filter from these 500. So what this means is that these 290 infrequent concepts we have in Let-It-Wag are not just the least frequent, they're actually the least frequent with respect to some diversity metric. So that's the sort of diversification step we took for curating these concepts. And then the second part of it was where we needed to meticulously scrape internet data to create a test set. For this, we took a bunch of different steps, and this is very nicely outlined in the paper appendix, but I'll give you a quick walkthrough. What we did was we collected different images by prompting on the search engines. For each concept, we had like, I think 4 or 5 different prompts so that we would get a diverse set of domains and distribution shifts in the images, as well as a different search engine for each of these. Because we noticed that if you actually had different search engines, the distribution you were capturing was actually very different. And funnily, actually, we also had a manual curation step in this. So what I noticed while doing the manual curation myself, I was looking through maybe 100K images myself every day. I noticed that I could very easily see which image was coming from which search engine because there was a clear demarcation of distribution shift just by search engine. And this was something that I looked through the literature and found that there's a lot of work on figuring out dataset biases from 2011, 2015, and so on. And even to this day, we still don't know how to tackle dataset biases, and they're still prevalent. So we had to do this like diversification on search engines, and then we had another filter such that we would only take images after 2023 so that they are not in the pre-training data sets of these models. Further, we did decontamination with respect to the test sets themselves, and then also looked at how close these particular images were with respect to each other so as to have an sort of a diverse set of images. So in general, this was, I think, a very tedious process, but overall, we have now, I can confidently say, a test set that captures the long tail well. And we also have statistics about how long tail the data distribution of this data set truly is in the paper.
Gonna have to just I promised myself I wouldn't do this during these NeurIPS pre-shows, but it seems like you would have benefited from using like 51, the library 51 to parse through all of the images. A little self promo there. But yeah, in section H of the appendix, for those that are listening, they highlight kind of their curation process as well as like, the different concepts that they have. So very well done there. I'm wondering, like you mentioned, there's some automated methods, manual kind of verifications that you have to do. Is it possible if, and apologies if it's kind of a redundant question here, but if you can give like a more detailed breakdown of like the automated tasks versus those that required human intervention, and kind of when you're deciding when to automate something, when to kind of do something manual, like what considerations were you making when you're making that decision?
Yeah, so when obviously nobody really likes to do a lot of data parsing, right? So it's a very tedious task and it can be quite boring. So we were trying to get away with automated curation as much as possible, but we quickly realized that this is not as easy as we talk about it. So the things we tried to do automatedly were very simple things like deduplication, for example, removing all the samples that are duplicates in this, because like I said, there are multiple search engines and we could have different hits and so on. The other thing that could be done easily automatically was to sort of figure out how close these images are to the pre-training embeddings. So what we did was we took all the pre-training embeddings of Lion 400 million and made sure that these images were not as close as possible to the pre-training data set. So they were diverse enough and decontaminated. However, even beyond this, since all of these are model-based or embedding-based automated curation strategies, there's a lot of blind spots that can go in. And a simple quick look through the images taught us that this is not going to be possible. So hence, I think we got a lot of false negatives in our curation process, which we had to actually remove through manual inspection. So overall, I think every pipeline that has like an automated curation would definitely benefit from a proper thorough manual inspection, more so for a test set than for a pre-training data set. Because for a pre-training data set, it's fine if you have some duplicates in there or whatever, but a test set really needs to be thorough because you want it to last long.
Personally,
Yeah.
something that I've seen people do quite often is when they're trying to deduplicate, they'll use clip embeddings as the signal for trying to get things that are not within a certain radius of each other. But in this case, if you're trying to evaluate the generalizability of clip style models, then there's somewhat of a conundrum there. So that makes sense.
Exactly. Yeah, totally agree. Yeah.
Yeah, in this paper, you mentioned that you used the inception net to kind of compute the embeddings for images. I'm wondering, like, did you do any ablations to test different models, or like what was the driving factor behind using inception net? That's a old school OG model. So
yeah, honestly, I think we ran like 2 ablations on this, but honestly, the only reason we used Inception Net was because it was easily available on an open source library. It could be that if you used, I don't know, Dino V2 or something like this, it probably might have given us better results. But yeah, I'm not so sure what that gap would be. But I still think even if we used a different model, we would still have to do the curation ourselves by hand. But yeah, the honest answer is it was easily available, so we just did it.
Yeah, Dino V2 would probably take forever to compute all those embeddings. That thing's massive. But yeah, dude, you guys would have absolutely loved using like 51 for this, because like the open source library. Nope, I'll have to edit that part out. Sorry. The open source library, you can like do things like compute embeddings, get representativeness, computer representative score, similarity score, uniqueness, and things like that. I mean, enough the self promo there, but I'm wondering, like, I guess when we're talking about similarity, what were there any kind of specific techniques that you use to measure and control for similarity? And I guess if you can go a little bit deeper in how you ensured that the Let-It-Wag data set kind of had minimal overlap with the images that were used to actually in those pre-training data sets, and like the models that you evaluated, for the models that you evaluated.
Yeah, so I think there's two notions of similarity here. One is for the Let-It-Wag dataset specifically, which you are asking about, but I'd also like to talk about this control experiment we did, where we looked at removing samples which were very similar to pre-training data, right? Because this was one of the confounders that people would ask us about. So here what we did was, there was this previous paper where they talked about this generalization gap of CLIP models. And what they saw was, if you just took ImageNet distribution shift test sets, embedded them, and looked at CLIP embedding distance with pre-training datasets, these are almost exactly in the pre-training dataset. So for this experiment, what we did was to simply take their pipeline. So again, remember that this is a CLIP model doing this embedding distance. So in some sense, here we want this, right? Because we want to remove the confounders from our CLIP experiment. And then we essentially removed all those samples from the pre-training dataset and then retrained the model on these sort of decontaminated training splits, and then got these curves. So that's the first similarity deduplication that we had to do. The second deduplication step, which was to sort of ensure that Let-It-Wag is not in the pre-training dataset. Some of these I already mentioned, where we tried to have a temporal filtering, because we know that all of these datasets curated before 2023. So we only took images after 2023 when we were searching for hits on search engines. And then the second, I think, more important filtering step which we did was this decontamination with respect to looking at the embeddings from the pre-trained models of Lion 400 million. So we took Lion 400 million, again, a reasonable proxy, but not the best, because there are more image text datasets out there. And we saw that if a particular image is within a particular gap of the pre-trained dataset, we remove them. And this was done again with a CLIP embedding, essentially. So these were the sort of, I mean, note that they're similar, but not exactly the same, because in the first one, we could afford lower recall, but here we wanted really high recall so that we get a diverse set of samples. And that's the overall pipeline, essentially, for the automated curation steps.
Awesome. Thank you. Do you have any, I mean, you look like you became like an expert in data curation and building these pipelines for constructing a Let-It-Wag. I'm wondering if you have any like words of wisdom or actionable takeaways for people listening that they can kind of use in their own day-to-day work.
So I think one very key learning for me from this, obviously people know in general know that data is king. I mean, models are what they eat and so on. So I'm not going to talk about that, but I'm going to talk about more like an infrastructural thing I learned along the way, which is that obviously when you do data research, data-centric research, you have to look at a lot of samples. Definitely spend some time investing in like creating an infrastructure where you can do data curation easily. So in our case, we built like a small app where we could quickly discard out samples and so on. And I think we spent about a couple of days building this. And if we did not do that, I guarantee you we would have pulled our hairs out. So definitely when you're doing data-centric research, I think it's good to just spend some time thinking about what problem you're trying to solve with respect to the manual curation and just create an optimized pipeline for this.
Yeah, one of our
favorite
slogans.
saying is, data eats models for lunch.
Yeah.
I love that. Yeah.
Yeah. So if you're going to be in Vancouver, come swing by the Voxel 51 booth. I'll hook you up with a shirt and some stickers that say this: data eats models for lunch. Vishal, thank you so much for joining and for chatting with us. I appreciate you taking the time out. And I look forward to meeting you in Vancouver. Will you be there?
Yeah, I'll be there. Looking
Awesome.
forward to meeting you guys. Yeah.
Awesome. Cheers. Take care.
Awesome. Thank you so much.